Hello class, Dr. Vance here. So let's continue our discussions on the properties of Fourier transforms. This shall be the part 7 of this particular lecture on the properties of Fourier transforms. So in this one, this is going to be our 14th property, which is the autocorrelation property. So autocorrelation property. Alright, so now this shall be our last property to consider. Okay, so now if x of t is the Fourier transform for x of omega, then the autocorrelation, which is r of what? T, will be the Fourier transform, okay, for the spectral density. Okay, this is the spectral density, and I'm sure you saw the spectral density in our previous discussion in Parseval's property. Okay, in Parseval's property, we got the spectral density, which is the distribution of the energy over the frequency. Okay, so then we're going to have this one. So basically, this one is the autocorrelation of x. Autocorrelation, okay, of x of t. And this one is the spectral density, the energy spectral density. Okay, which is the distribution of the energy over the frequency. Okay, so let's define our R of t. Okay, so sorry, it's not R of t, it's R of tau. Okay, so our R of tau here, okay, is actually equals to integral infinity to minus infinity to infinity. Okay, x of what? T into x of complex conjugate t minus what? Tau. Okay, dt. Alright. Okay, so basically this is the definition, okay, for the autocorrelation of x of t. Okay, so now the Fourier transform of r of tau, which is the autocorrelation, is going to be, okay, like this, minus infinity to infinity, r of what? Tau. Okay, r of tau into e minus j omega what? Omega tau d what? D tau. Okay. Okay. So now, if I should expand and introduce in the r of tau, okay, then I'll have infinity minus infinity. Okay. Here, infinity minus infinity. Okay, x of what? Tau into x of what? Complex conjugate. Okay, complex conjugate what? T minus what? Tau. Okay, t minus tau d what? D tau. Okay, so this is what we're going to have. Okay, and then I'll have this one. Okay, so if I should expand, this is what I am actually going to what? Have. This is the tau. Okay, it's the tau. Now, if I should actually say that t minus my t minus tau here, okay, my t minus tau here, if I should say that is equals to what? P. Okay, then that means that t minus p is equals to what? Tau. Okay, and that would also means that minus or the tau is equals to minus what? dp. Okay, the tau will actually mean what? dp. And this will also mean that as tau is approaching infinity, approaching minus infinity. And as tau approaches minus infinity, P will be approaching infinity. Okay, so now from here, if I should introduce these ones into my equation, then it will now become here infinity minus infinity. Okay, okay, I can see that x of what? T is here. Okay, x of t is here, dt. And then I can say that here, like this. Okay, this t minus tau, okay, it will change, all right? It will change to this t minus tau will change. It will change to what? It will change to p. Okay, it will change to p. So s complex conjugate of what? P into e minus j omega. This tau, it will become what? It will become t minus p. Okay, it will become t minus what? Minus p. Sorry. It will become t minus what? P. Okay. And then what I'm going to have here is that I'm actually going to have the p. Okay, I'm actually going to have the p. Okay. And then you see, we say that whenever we say that the tau is equals to what? Minus dp. Okay, the tau is equals to minus dp. So here is what? The tau. So it must be what? Minus dp. But I cannot write minus what? Dp. But it would rather affect what? The limit. So here will become what? Positive. And here will become what? Negative in this instance. Okay. And then we said that when tau is approaching infinity, p will be approaching what? Minus what? Infinity. Okay, so that means that if this one is going positive, they are becoming what? Negative. So the whole equation will be affected by this one, negative. Okay, so let me rewrite it again for you to see. So this is how it will be. Negative here, x of t into dt. And here, positive infinity to minus infinity, s complex conjugate, p, e minus j omega, t minus p, d what? dp. Okay, so that is what I'm actually going to have here. Alright, so now, you see this negative here, okay, this negative here. If I change this limit, then this negative must become positive. Okay, so in that case, the function will still change again into here infinity minus infinity. Okay, x of what? T into what? dt. Okay, so now I'm making here, instead of negative, I'm making it positive. That will affect this particular limit, and then this limit will now come back to its original state, minus infinity to what? Infinity. S complex conjugate of what? P into E minus J omega T minus what? P into what? dP. Okay, all right. So now, when I have that, what I can say is that I can now have the Fourier transform of R of what? Tau to be equals to, okay, to be equals to this. So now because infinity minus infinity, okay, x of what? T dt. Okay, x of t dt. Oh, sorry. Let me not bring a t like that. Let me bring it here e. Okay, here let me bring it e. Okay, minus j omega. Okay, t. Okay, and then here it will be what? The t. And then here it will be minus infinity to what? Infinity. S complex what conjugate of what P into E, okay, into E minus, okay, into E, which is going to be positive, I think from the previous one, then I'll have positive J omega P, okay, yeah, positive J omega P, okay, into what? Into the what? dP, okay, into dP. Alright, so now what I can say is that this Fourier transform, okay, this Fourier transform of what? Of the autocorrelation is now going to be equals to integral infinity minus infinity x of what? T into E minus what? J omega T, okay, dt, alright, dt into what? I'm just rewriting this one for you to see, okay, minus what? This one into S complex what? Conjugate of what? P into what? E minus what? J omega what? P d what? dP. Now, if I bring this complex conjugate outside, then this negative will sorry. It's positive, right? I don't have to make it negative. It's positive. From here, it's positive, okay? Why am I saying it is positive? Okay, it is positive because if you come here, minus J omega times minus P, if you expand, you get what? J omega what? P, all right? So that is why I am saying it is what? Positive, okay? So please, I'm sorry, here is positive, so it's positive here. Let me rewrite it again, sorry. So Ft into R of what? Tau into this, okay, is equals to this, is equals to this, is equals to x of what? T into E minus J omega what? T, the what? The T into what? This, into minus this, into x, okay, of what? P into what? E, J, P, d what? dP. Now, let me bring the complex conjugate outside. In that case, it's going to be like this. Here, all right, like this. X of what? T. Okay, x of what? T. X of T into E minus J T into what? dt into like this. Okay, into x of what? P into what? E minus J omega what? P. In that case, I bring the complex conjugate outside. Okay, into what? Into dP. Alright, so now from here, what you can see is that the Fourier transform of R of what? Tau, okay, is now going to be, this one is nothing but what? Is a formula for what? Fourier transform, which will give you what? X of what? Omega. Okay, so now here I'll have what? X of what? Omega. This one is also what? The Fourier transform, which gives you what? X of omega. So now X of what? Omega. But this one, the conjugate is here. So I'll bring that conjugate here. So now this is the end of it. So now the Fourier transform of autocorrelation is what? X of what? Omega into X of what? Omega. Here is the correlation. Now, in case, let's say X of T is the same. In case you see that the name is what? Autocorrelation. That means that it is actually with itself. Okay, so in case like as we started, okay, let's say this one and this one are the same. Okay, this one and this one are the same. All right, then we're going to have f of what? T, R of what? Tau. Okay, it's going to be like this, a square of itself. Okay, all right, so that is what we're going to have. And then what I can now write it is that the autocorrelation is now a Fourier transform of this particular format, which gives the energy what? Spectrum. Okay, so here like this. Okay, Okay, and this one is what? Autocorrelation. Autocorrelation. Autocorrelation of what? X of t. And this one is the energy spectral density. Okay. All right. So this is the end of this particular property. Okay. Oh, sorry. I didn't know you were not seeing. All right. So I'll see you in the applications. This is the end of the properties of Fourier transforms. Thank you so much.